So this afternoon, Adam Smith, as you can see, is going to continue and start to dig down into more details into the sorts of issues we were discussing.
All right. So
I love the fun.
this is like a couple of hours of well-spent time right there.
Next slide, please.
Okay. So this talk is about privacy in statistical databases, which makes sense for the workshop and the program. So for now, we're going to consider the following sort of stylized and simple setting, and we'll sort of see departures from it at various points. But imagine that we've got a bunch of individuals who contribute data to some central collection managed by some server or some agency or server that collects this data, and we'll call that agent the curator. And the idea is to make this data available for public use possibly by publishing things about the data set, possibly by answering queries about the data set, but basically to make as much sort of statistical information about this data available as possible. And we'll be interested in the case where the information that's being collected is itself sensitive. Large collections of personal information are essentially ubiquitous now, and of course they've been increasing in both their size and their value over the past decades. And here are a few examples of applications where this comes up. All right. So we've got these two conflicting goals. On one hand, we want to get as much information as we can out of the data set. And on the other hand, we want to provide some guarantee of privacy to the individuals whose information is contained in the data set. And intuitively what we want is that individual level information should stay hidden while kind of global features of the data set should be available. And the question we'll be asking for the first part of this tutorial is, how can we define these terms precisely? And I claim that utility is the thing that most of us are used to thinking about. If you take a statistics class or a data mining or machine learning class, you think about various measures of utility. There are many different measures, but it's sort of a relatively well thought through question. Whereas privacy is something that is significantly less well understood. So variations on this question have been studied in statistics and information theory and the data mining and database literature, also in cryptography, starting from, I would say, the 1960s. And in the last 10, 15 years, there's been a lot of emphasis on trying to pin these questions down more precisely, and I'll talk about that. Okay, so some caveats. This is a tutorial. So this is not a survey. It's necessarily incomplete. There's way more to talk about than I can possibly cover. In particular, if I don't cite your or my work, forgive me, unless I really screw up and misattribute something, in which case, let me know. It's not a broadcast. If you want to watch the live stream, you can go upstairs and watch it. But since you're in the room, please ask questions. I have far more material than I can present in 3 hours, and it'll be much more productive if there's interaction. You'll get a lot more out of it, and I will have more fun. So finally, before I really dive into it, just to give you some resources that this is stuff you want to know more about, you might want to look into. Cynthia Dwork and Aaron Roth have a nice monograph. It's somewhere between a tutorial and a textbook called Algorithmic Foundations of Data Privacy. Salil Vadan has a survey monograph thing that he wrote recently that's forthcoming called The Complexity of Differential Privacy, which focuses more on computational complexity issues. There's a workshop, a bunch of tutorial videos from a 2012 DIMAX workshop that are those are all online. There are lectures by Moritz Hart, Aaron Roth, Benjamin Pierce, and Jerome Miklau, and also videos of tutorials and talks from a 2013 workshop at the Simons Institute in Berkeley with a nice tutorial by Katrina, among other things. So these are all nice resources to know about.
That second one is a survey. It's a book, isn't it?
Well, it's a long thing.
It's shorter than what most people would call a book, and it's a beautiful survey, and I think it's posted already.
Is it now public? I don't know. So I've seen a copy, but it was. Sorry.
It's specific to complexity theory.
Right. It's a survey, but it's a long one. I mean, it's not a. It's almost a tutorial.
It's based on a full week of lectures, many hours a day, in at an institute in Barbados.
Right. So yeah, I've seen a copy, but I don't know if you say it's on the web now, then that's great. Okay, so keeping with the font, we'll have 3 episodes numbered 4, 5, and 6. So the first one will be called, will be about sort of attacks and this notion of differential privacy. Second one, we'll see some basic algorithmic tools, and we'll try to apply them. And the last one, we'll talk about connections to other areas, and this is all as time permits. Okay, so episode 4, right? I was tempted to call this A New Hope, but that sounds a little pretentious. All right, so first part is let's try and understand why this question is challenging. Why is it that pinning down the notion of aggregate is delicate? And then I'll talk about this notion of differential privacy. Okay, so let's start with that. Okay, so in some sense, one of the things that makes reasoning about privacy very challenging is that in addition to the information you have the data set you have, there's all this other information about people out there. Users of your data set, of your data products, may have access to other information about the individuals in your data set. You certainly can't assume that you know that you know what they know, never mind what they might know in the future, right? And roughly as a result of this issue, anonymized data sets, there are lots of examples of things going wrong with supposedly anonymized data, and basically making data, quote, anonymous is extremely tricky. This is an example that you may have seen before. In 2006, as part of a competition to improve its recommendation system, Netflix released a data set of, it was a subset of its users and a subset of movies, reviews those users had given the movies. All identifying information, obviously identifying information for users was removed. All that were left, just random identifiers were left for the users. Two researchers at who were both at the University of Texas at the time correlated this anonymized data with some public and much less complete data from the website IMDb, which is a website where people go and enter reviews about movies and discuss movies. And the point is that on IMDb, there's sort of less information, but it's associated to people's actual names. There's actual information about the users publicly available there. And they were able to match up a lot of the people in IMDb with the Netflix data. Not surprisingly, IMDb users heavily subscribe to Netflix. And they were able to re-identify a big fraction of the people in the IMDb data set, or to link their identities to anonymized records in the Netflix data. And of course, the point is that on IMDb, you discuss all the movies you want everybody to know you watched, and on the Netflix data set contains, a bunch of the movies you watched. Yeah?
Just a question about terminology. I think there is often a different use in Europe and in the United States of the word anonymized.
Mm-hmm.
In this context, anonymization means just suppressing identifiers, I guess.
Well, okay, so so Netflix, what Netflix had done is they had removed identifiers. They just left the reviews. I mean, not the scores and maybe approximate dates.
Yeah.
Not the text of the reviews.
So here we call doing this de-identification, and anonymization is something more. And I guess
Okay.
that the United States is just the other way around.
So I guess perhaps the right term is de-identified. The point is that the people at Netflix assume that this data was anonymized, whether or not it was. I mean, and the point is that it wasn't, right? I guess that's my, that's the context of this statement, right? Is that just the notion of what constitutes anonymized is not itself obvious.
The columns here are movies?
The columns here are movies, and that's right, and the rows are people.
So how many movies did it take more or less to identify?
Well, okay, so there were, I forget the number of movies that were in the data set, thousands, I would assume. This is a quote from one of the authors who said that on average it takes about 4 movies to uniquely identify a person. But that means, that is, there exist 4 movies that more or less uniquely identify you. Because most of us watch a small number of, random movies that few other people watch, and those few movies, that pattern, more or less
How many people
identifies.
were in the file?
How many people, do you remember how many people?
480,000.
480,000 users, is that right? And how many movies? Thousands, I would assume.
Remember.
Yeah, I could look, we could look in the paper for the exact number.
Because with 4 columns, there's only 16.
No, so the idea is that, yeah, this statement is a weird one. This statement is that, for each person there exists a set of 4 columns in which they're, or for most people there exists a set of 4 columns in which they're unique. Right.
Ah, I see.
Right, which is a different statement than saying there's one set of 4 columns that identifies everybody. Right. Okay, and there are lots of sort of published examples of things along these lines where data sets that were prepared for the purposes of release with the idea in mind that they would be anonymous turned out to not be. Turned out to be relatively easy to re-identify. There were examples based on social networks, examples based on computer network traces where people were able to sort of reconstruct the internal structure of a network, based on micro-targeted advertising, recommendation systems, some stuff with genomic data, based on composition problems, which is, so suppose you've got two hospitals that serve overlapping populations that release information, supposedly anonymized information about, independently release information about their populations, which is possible to afterwards correlate. And I omitted citations from this slide just because I ran out of space. There were lots of them. I have older versions of this slide where I had all the citations, but then it got too crowded. Okay, so I guess I don't want to spend a lot of time on this, but it's an important point that maybe came up earlier, and so I'll dwell on it just a little bit. Is that the kind of when people talk about naively de-identifying information, they normally think of sort of information about people as divided into 2 categories: identifying information and non-identifying information. Right? And something like movie reviews would be considered non-identifying information. Something like names and addresses are considered identifying information. But actually, my name, Adam Smith, is much less identifying than the set of reviews I've made on Netflix. And the point is that it's very difficult to categorize information in this way. The authors of the Netflix paper dubbed this the myth of PII, which I like the phrase. Okay, so based on the kinds of examples I was discussing, one might conjecture that the problem is granularity. That in some sense, the issue is that if you release individual level information, it's going to be possible to potentially possible to link individual records in one source to individual records in another. And so you might think that, in fact, a safe solution to this is to somehow not release information that is granular in this way, to only release aggregate information. And I'd like to sort of convince you over the next 20 minutes or so that even that goal is not so obvious. It's not obvious how to achieve that. And the point is that defining the notion of aggregate is very delicate. So here's an example. A support vector machine. This is a support vector machine isn't a machine at all. It's an optimization problem. It's just a way of fitting kind of a classifier to a set of data points with binary labels. But roughly speaking, it's a way in 2 dimensions. It's a way of coming up with a line that separates 2 sets of points as well, reasonably well. It's the result of some global optimization using all the points in the data set. But at the end of the day, the standard format for representing the output of this process is this line is represented by a subset of the data points that define it, called the support vectors. And those data points are kind of released in the clear as part of the description of the line. Okay? So you could just release the parameters that define the line, the equation that defines the line, but the sort of standard way to think of the output of the support vector machine is in its dual form, in which case you're providing these points, in this case 3 points explicit.
You mean if I knew the line, I would know these points?
No, that's not true, but the standard way of representing the line includes more information than that. But the point is that it is the output, the result of this sort of very aggregate processing of the data, and yet it contains these points, and that might not be obvious from just an inspection of the output. Maybe another kind of example is, suppose I wanted to release related statistics. So suppose I consider releasing the number of Cantabrigians who voted leave in the recent referendum immediately before and after Chris Skinner moved to Cambridge for the semester. Then, by correlating these 2 statistics, I could figure out whether or not Chris voted leave in the most recent referendum, and perhaps if I were, a member of the next government, I might use that information to decide whether or not Chris should receive funding when the time he asks for it.
Did you get it? How?
Oh, so suppose I release the number of people who voted leave immediately before and after Chris moved here, right? So.
One referendum.
Huh? Oh, I'm sorry. Okay. Suppose I release 2 statistics. I release the number of people who leave. Maybe the example is too contrived. let me try a simpler one, and then the example will make more sense. Suppose I release the average salary of the people in this room, then I ask Chris to leave the room, and then we once again compute the average salary of all the people in the room. Okay? So then from these 2 statistics, I can easily figure out, and the number if I also know the number of people in the room, I can easily figure out Chris's salary, even though either of those statistics individually wouldn't release.
To repeat the referendum, which may occur.
We may well, right, let's not even go there. No, you don't, well, okay, yeah, whatever. Let's not beat this horse too much. All right. Okay, so this is like a very simple example, but there are much more interesting examples of how statistics taken together can encode a fair amount of data, and can encode essentially an entire data set. And sort of attacks that take advantage of that are sometimes called reconstruction attacks. And they have the broad interpretation, and I'll give you some examples, but they kind of, all of them have the same sort of English natural language interpretation, which is if you have too accurate statistics about a data set, eventually you'll be able to basically reconstruct the data set, even if each of those statistics individually seems very much an aggregate.
Before you leave that slide, I just want to say that you said it's hard to define aggregate. Also individual.
Similarly.
Is a kibbutz an individual, or?
Is a kibbutz as an individual? That's an interesting, yeah. So for the purposes of this talk, let's assume that there's a granularity which is clear, which we define as individual, but you're right that in general there could be kind of organizations or groups of people who we might want to hide information about, and I'll talk a little bit about that in a little later. Okay, so let's look at an example of reconstruction attacks. To do that, I'm going to sort of start with an abstract setting and try to specify it afterwards in a couple of different ways. So this is sort of roughly due to a paper of Denur and Nassim from 2003. Consider the following problem. Suppose there's a data set of n people, and there's some kind of secret vector. There's a secret bit associated to each person. So I've got some secret vector z, which consists of 1 bit per person. The data set may have other stuff in it, but there's some sort of target information z that I'm interested in learning. And imagine we've got an attacker who sees some information about z, and the information that the attacker gets to see is basically some kind of noisy linear function of this vector z. So there's some matrix Q, which is known to the attacker. We'll assume for now that all its entries are zeros and ones. And what the attacker gets to see is sort of this, the Q times Z, maybe divided by n, so all the entries lie between 0 and 1, that's right, plus some noise, which the attacker doesn't control, and all that we know is that the noise is such that every entry of the noise vector is less than some known number alpha. So the attacker gets Y, the attacker knows Q, the attacker knows alpha, and the question is under what conditions can they reconstruct all or most of Z. Okay? So under what conditions on Q and alpha can the attacker construct a vector Z such that the Hamming distance between Z and Z hat, Hamming distance between Z hat and Z goes to 0, so relative to n. So here the Hamming distance is the number of entries in which Z and Z hat differ.
M fixed here?
Let's think of n as fixed. N is the number of people. N is just is m fixed. So we're going to assume that m is sort of given. So when we ask under what conditions, the condition on Q might include how many columns it has in it. Yeah.
N is not fixed.
Sorry, rows.
Going to 0 here as n goes to infinity.
Sorry, now I understand your question. We will consider m growing with n and at various different rates, and we'll sort of, yeah. I don't want to specify a relationship between m and n. Okay, so where can this type of setting arise? One setting is where you've got a data set, much of which is public, but or not necessarily public, but known to an attacker, where there's one attribute that's considered that the attacker doesn't already know, or is considered sensitive. So imagine, for example, you've got the data set consists of 2 parts, a matrix A consisting of d bits per person, and those are known to an attacker a priori. And then Z is 1 bit per person that is secret. So now each person's data consists of d plus 1 bits. And suppose you want to start releasing information about the relationship between this attribute Z and these other attributes. So for example, you might want to release pairwise correlations between these attributes. If you sort of strip away sort of abstract what the information that the attacker is learning, what they're basically learning is for each of the columns of A, they're learning the inner product of the column AJ with Z. And we'll just normalize that by n. And so even if you're getting sort of noisy correlations, what you're learning are these noisy inner products. And then the matrix Q I had on that previous slide is now just A transpose, just the public part of it. Okay, or you could get a slightly more complicated example where you're releasing three-way marginal statistics about this table, in which case for every pair of columns AJ and AL, you would learn from the like a three-way contingency table, even if it's noisy, you would be able to learn. Roughly speaking, the inner product of Z with some vector which is an entry-wise product of AJ and AL, again normalized by n. And then the matrix of linear constraints that you're learning about Z is some weird product of A with itself. Okay, but it's some matrix again that's known to the attacker. And there are other examples. If you were to, for example, to release the result of doing trying to fit some regression model that predicts Z based on the attributes in A, again, you can interpret the information that's revealed as giving you, even if it's what's revealed is approximate, is giving you kind of noisy linear constraints on Z. A different flavor example where this comes out is where you've got an attacker who knows a superset of the data. So now you imagine that a superset of the data set is known to an attacker, and all they're interested in to figure out which rows of this bigger data set are present in your secret data, the sensitive data set. In which case, in that case, the secret vector Z is basically just an indicator vector for the actual data. It's sort of indicating, you know, you put a 1, my secret bit is 1 if I'm actually in the data set, and 0 otherwise. And then again, if I learn information about the secret data set for various natural kinds of statistics, I can interpret that as learning noisy linear information about Z. And so again, we get these sort of some kind of approximate linear constraint on Z. Where in this case, you know, reconstructing Z in this case is figuring out who is in the data set and who's not. Okay, we'll talk a little bit more about this type of attack later. But abstractly, all these situations I've just mentioned, they kind of fall into the same basic setting where what I'm learning are a bunch of linear constraints on this secret vector Z, and I want to know under what conditions I can reconstruct Z. So this is, you know, roughly speaking, the question posed by Dinur and Nissim. And one thing they looked at is, well, what if Q really has a lot of rows in it? What if Q contains sorry, the slide got messed up. What if Q contains all the possible questions, all the possible kind of binary linear combinations I could have asked? So it contains all possible Q in 0, 1 to the n. That's the thing that's missing. Okay, in that case, the number of rows in my matrix is exponential in n. And this sort of corresponds to any setting where I'd want to release enough information that you could ask for statistics on any subset of, you could ask for statistics on this secret attribute for any subset of the people. Okay. And it turns out that in that case, we can reconstruct a good approximation to Z anytime the statistics that are being provided are non-trivial. So let's just just to understand how to calibrate this, we've normalized these things so that Q times Z is or Z, sorry, is a vector of numbers between 0 and n. When I divide by n, I get a vector of numbers between 0 and 1. So you know, I'm releasing a sort of an approximate. If I release a non-trivial approximation, is anything where alpha is, you know, strictly less than 1. Ideally, you'd want more accurate statistics than that, but as soon as alpha is less than 1, you're getting something non-trivial. And in this condition, with this many queries, you can actually reconstruct Z anytime alpha is significantly less than 1, once it's about less than a quarter. Okay, and I'll just explain how that works. So the idea, what an attacker can do, given Y and this knowing this sort of matrix Q, which consists of all possible binary linear combinations, the attacker is just going to look for any vector Z hat which is consistent with the released statistics. Meaning, I'm sorry, there's a 1 over n missing right where the red laser pointer is. He's going to release something which is close to, so he's going to find a vector W of zeros and ones, which minimizes the distance between the release statistics and the statistics for W. Okay, so this is a natural candidate for Z. And it turns out that any Z hat for which this quantity is sufficiently small, is in fact going to be close to z. Okay, so in fact, if z hat is the actual minimizer, then the distance between z hat and z is going to be at most 4 alpha times n. And so as long as alpha is less than a quarter, then I'm starting to reconstruct entries of z. And as soon as alpha becomes less than an eighth, I'm reconstructing a majority of the entries of z. And as soon as if alpha is less than 1 in 20 or something, then I'm basically reconstructing all of z. Okay, and the argument for why this isn't very complicated. So the idea is that if I look at the Hamming distance between z hat and z, if z hat and z were far apart, if there were many entries on which they differed, then I could find a subset of positions where I could take my query to have ones on all the places where z hat is 1 and z is 0, or vice versa, where so if this is z and this is z hat, if their Hamming distance is far apart, there's going to be a large subset of positions, not necessarily contiguous, where one of them is 1 and the other is 0. And so I can look at what happens when I consider the query given by the vector q, which is just those positions in which they differ. And so it's going to have a bunch of 1s in the positions where z and z hat differ. And basically, if their Hamming distance is large, then this will be a query where there's a big difference between the answer to the query on z hat and the answer to the query on z. Okay, so I can find a vector q such that this difference is large. And in fact, I can always get something that's within a factor of 2 of the Hamming distance by choosing there's either going to be more places where z hat has 1s and z has 0s, or the other way around. And sorry, I skipped a step here. So what we know is that we know that q times z, or 1 over q times z, is very close to y, just because y is provides accurate information about z. We also know that 1 over n times q times z hat is very close to y, because of the way we constructed z hat as the kind of best fit we could find. And so just by the triangle inequality, we know that I can upper bound this Hamming distance by 2 terms, each of which is at most alpha times n, or sorry, I can upper bound this maximum by 2 terms, each of which is most alpha times n. And so I get it, then I get to pick up an extra factor of 2 over here, and I wind up with an upper bound of 4 alpha n. Okay? And all that's going on is that I've got so much information about z that anything which is sort of consistent with any binary vector which is consistent with the information I've released is going to be close to z. So what does this say? It means that it would be nice if we could release some sort of synopsis about z that allowed us to answer any question we wanted about z. You know, to allow us to ask for statistics on any subset of the rows of z. Right? I might maybe, if z is an indicator of who's diabetic and who's not, I might want to be able to ask for statistics on the fraction of diabetics in whichever subset of the population I want. And what this type of argument shows is that you can't hope to do that without basically releasing all the information. Okay. Right, so that's what I just said. This is sort of an extreme example. The number of things I'm releasing about z is absolutely huge, right? I'm giving you information on all possible statistics about z. On the other hand, I'm giving you a very weak guarantee on how accurate they are. I'm just saying, in order for this attack to work, I just have to give you, we're looking at proportions that are within, let's say 1 in 10 of their correct value, which is a very, very crude approximation. So if you get more accurate statistics, you can do far more. And there's actually a fair amount of literature on exactly what the trade-off is between how accurate the statistics are and what they look like, and how easy it is to reconstruct information based on this. But one example is what if the number of statistics we're releasing is not 2 to the n, but more like n, right? Something much smaller. Then there's basically a general strategy that works pretty well, and a lot of the attacks in the literature basically have this form. I'll look for some data set that again minimizes some measure of distance between the vector of statistics that were released, that's y, and the vector of statistics for that data set for some measure of distance, usually like the Euclidean distance or the L1 distance. And that'll give me some kind of approximation to z hat. Maybe that consists of numbers between 0 and 1, or -1 and this. Sorry, this should be a 0 and 1. And then I'll just, to get a guess at z hat, I'll just round each of the entries of that vector to the nearest integer.
If Q is invertible, then you can just solve it.
If Q is invertible, you could just try to solve. So actually that sometimes works too, although here, so if Q is invertible, I'll get to that in a second, but notice that because I've got an error term, it's actually just invertibility isn't enough, because I want something that works.
Equation, you're ignoring the error also here. Minimize.
Yes, yeah, to solve, okay. Solving this minimization problem, if Q is invertible, there's a unique solution. In general, even if Q is not invertible, one can still solve this equation relatively easily, solve this optimization problem relatively easily. Right? So this is this is a convex optimization problem, or it can be transformed into a convex optimization problem. It's relatively easy to solve.
You get to choose Q, so I would choose.
You don't necessarily get to choose Q. So, for example, in the examples I gave you earlier, Q is determined by the person who's releasing information, not necessarily by the attacker. Okay. But one sort of phenomenon that occurs with these types of attacks is that if the number of statistics you're releasing is greater than the number of people in the group about which the statistics are provided, and the matrix of these linear constraints is nice in some sense, then you get then the Hamming distance between the release statistics and the true ones, the reconstructed vector and the true one, goes to 0 at a rate of about alpha squared n. So as soon as alpha is less than about 1 over squared of n, I'm sorry, there's another typo, the 1 over missing here, the error goes to 0. And so what this sort of gives us, two extremes. One is when we've got lots of queries, then the error. I'm sorry, I switched from one normalization to another with these slides, and I obviously didn't propagate the change properly.
How do we feel when we read sequences of papers in this literature?
Right. me too, sometimes. But okay. Let me try this. Let me try to say that what I want to make the point I wanted to make concisely. Essentially, what's going on here is that as long as so as soon as the accuracy with which I'm providing these statistics goes to 0 quickly, once that they're sufficiently accurate, and sufficiently accurate for a lot of these contexts means error less than about 1 over squared of n, so error that's really kind of just below what the amount of error you'd expect due to random sampling. For example, if your data set were a sample from some larger population, you'd expect, depending on various things, about error 1 over squared of n in the estimation of various proportions. if the accuracy of the statistics that's being released is significantly below that, that sampling error, which is normally what you'd want in order for them to be useful, then then given sufficiently many statistics, that is more than the size of the group about which you're providing them, you'll be able to kind of reconstruct almost all of this vector. Okay, and there's some very nice connections in this literature to compressed sensing and discrepancy theory that I'm not going to go into. But maybe the thing to kind of take away from this is that, again, if you're going to provide if you're going to provide something that is useful for many different purposes, and you're providing something providing statistics that are relatively accurate, then at some point you're going to hit a point where you're basically providing the entire data in the clear. Okay? And so if you so even though each of the things you're providing, each of the entries of this vector is some kind of sort of aggregate noisy statistic, taken together, they encode the entire data set. Okay, so I'm not going to go into too much detail. I won't give you the example. I had an example prepared, but I'll move on. Yeah.
Let's go back to the slide you were on for a few seconds.
Sure.
I believe the implications of the rough rule took a long time to sink in. And in particular, things like public use microsamples, which have M very much bigger than Cn all the time, were produced since the early 1960s. And the implications of this research on the ability to protect privacy in those files has never really fully sunk in.
Yeah, so
no one's even pretending that it was a summary statistic. For the most part, it's the answer that was on the survey form, anonymized in the sense that it shows up,
right,
used it, and then released.
Right. So I guess the point of these examples is, and I mean, yeah, I could work through the math on more of them, but maybe that's not the point, as you're saying. Somehow the larger point is the more important one.
It was really addressed to you. It was addressed to my colleagues in the room.
Right. So let me try to sort of repeat it. Is that if you want to release one thing, which is useful for everybody, you're in trouble. Okay? That anytime you're releasing like one object which is going to be useful for many purposes, you're going to have to pick and choose. You cannot provide something that is useful for all possible purposes without basically providing the data raw. And that is essentially the natural language lesson I draw from these examples. And I wanted to kind of step through the mathematics of at least one of these examples just to kind of give you a sense of what's going on. And I'm happy to go more slowly or more quickly, depending on what people want. But hopefully the larger point is clear here. I'm not sure. Yeah, Chris.
Following from what John said, I mean, my interpretation is why people argued for releasing full microdata sets was because there were multiple uses, and the only way you could meet all those uses is to provide effectively the full vectors. Can I just ask about the identification issue? I mean,
sure.
I know there are, presumably that's another argument in terms of linking these to known individuals. Where the Z is in this case, the sort of identifier which isn't of interest directly in the statistical outputs. I take the point you've been arguing, which I think is very well done in terms of the aggregates actually leading to effectively the release of something very close to the full microdata. But can you just say something about the identification step as well?
So, okay, so what maybe the right way to think of the sort of setting I was just working through is a somewhat, a somewhat stylized setting where you're saying that the information that you're worried about reconstructing is just 1 bit per person, and you want to know under what conditions can I provide statistics about that bit vector without basically releasing that vector. Now, the question of how that's connected to identification is, so that this sort of stylized setting is a couple of steps away from, real life, of course. That's what stylized means. So what's the right way to think about it? Well, so I would come back to those. Okay, so I had on a couple of slides, I had sort of the type of setting where this might arise. But yeah, I'll just keep the picture up. Maybe. So, one example is where what is known is like there's a set of people, and I'm providing there's a subset of them about whom I'm providing these statistics. And now in this particular case, what these attacks would allow you to do is to figure out exactly which subset of them is being analyzed. Like if I'm providing statistics about the diabetics in the population, in the group, then what you're reconstructing is exactly who's in that subset, who's diabetic, right? So I'm not sure if this really answers your question. In the sense that I guess I don't think of re-identification is fundamentally any different from any other type of leaking information about people. I guess to connect this setting specifically to re-identification, the connection makes most sense when you're in an environment where the attacker already knows a fair bit about the data set, right? As in this example. But
one way to answer, if you have a list of people who voted in England recently, which probably exists somewhere, but you don't know how they voted, with 2 questions with you and without you in wherever you voted, I know how you voted. And with enough questions, he's saying that you know everyone.
Yeah, okay.
Right, yeah, and maybe the point is that with enough questions, it doesn't matter whether or not those statistics are exact. So in order to figure out whether or not, John voted from these 2 statistics, those have to be exact counts for me to take the difference and learn something meaningful.
If the noise is a quarter,
right?
With 2 questions, I know exactly how he voted.
Right, but now we're saying, well, what if the noise is within, what if I'm providing these statistics within 10%? I'm providing them only with accuracy 10%, right? Far less than the accuracy necessary to distinguish between what people thought the outcome of the referendum was going to be a week before the referendum and what it actually tended out to be, right? Even at that level of granularity, with enough statistics, you basically can reconstruct the entire vector of the way everybody voted. Or not everybody, almost everybody, right? Sorry?
The statistics can be big sets of people.
The statistics can be about, arbitrary subsets of this population.
No, I mean, making the point is that we're not talking about really clever differencing attacks where it's n versus n minus 1, but just large overlapping subsets.
Right. Yeah, so I guess I didn't, abstractly you can ask, what do I need to know for the subsets about which I'm getting information, what sorts of subsets cause problems? Sorry, I'm going to skip ahead. I'm sorry if this is giving you a headache. But what kinds of matrices do these attacks apply to? And the answer is pretty much everything. So random, if the matrix, even if you just ask random queries, it actually works very well. There are sort of, and people have worked on, characterizing the algebraic properties that are necessary for this type of attack to work. But the point is that, they work for lots of natural classes of matrices that would actually arise.
This is just a special kind of inverse problem, isn't it? It's like
It is,
bias
yeah.
scanning or anything.
Well, that's. I was saying there's sort of nice connections to, compressed sensing and discrepancy theory and stuff. These are problems that come up in, we're trying to solve a noisy system of linear equations. Turns out we've been trying to do that for, 200 years, and so, since Gauss. And so, at this point, there are lots of tools out there to go and, hammer on this problem with, and that's indeed what people have done.
Are you sure Euclid didn't try?
You got me. Newton, certainly. I mean, Joseph.
Yeah, I think that there is some similarity between what you expose here and some noise filtering attacks that have been proposed, I think, by Agrawal and others in 2000, more or less.
So I focused on just one attack, right? But yeah, there are a lot of things, and a lot of, the ones I kind of pay most attention to, for sort of professional, the ones that come to my attention most easily are ones where there's a kind of a rigorous analysis associated to it, a proof that under conditions under which the attack works. But actually, there's an even larger literature of just sort of empirical examples of how people have, of carrying out attacks of this nature, and I'm sure there are far more than I know about, and certainly more than I could fit in this talk.
Then the attack works best when the data have been optimally protected to preserve a certain data use, or isn't that the case?
The more accurate the statistics you provide, the better these attacks work, not surprisingly, yeah, in general.
Then in general, if you want to release some data set for exploratory data analysis, which is more or less okay according to some general utility measures, which is the case in practice, then what would be the...
You're in trouble.
Well, but this is what...
I understand. And
people want.
Actually, but this is exactly the point, that releasing information for that kind of exploratory data analysis for a sufficiently general definition of exploratory is impossible without just releasing the raw data. That's the interpretation of these results. So, in fact, I guess the question I would like to pose, or the question that these results raise is, great, then what can we do? For which types of analyses can we provide accurate answers, and at what level of accuracy, and what's the guarantee we can provide? And that's sort of what the remaining, 2.x hours are about. So I'm going to charge forward. But yeah, Cynthia, you look like you were going to jump in.
I would just like you to introduce the fundamental law
Oh, yeah. So,
of information recovery.
so what Cynthia calls the fundamental law of information recovery is this point I articulated earlier, which is that too accurate statistics basically allow you to reconstruct the entire data. And if data set, if you want to, maybe I'm not articulating it the way you'd like to. But
Overly accurate estimates of too many statistics can completely destroy privacy.
there you go.
Yeah, but I mean, at this point there are two possibilities. One is nihilism, saying since we cannot do anything, let's not do anything at all.
Mm-hmm.
And the other is to just refuse to publish data for exploratory analysis, which is not going to happen because the big data community are not going to stop. So then, yeah, I mean, perfection is impossible, as you mentioned, but then the only realistic option is to renounce any privacy.
So what these attacks show is that not only is perfection impossible, but near perfection. Highly accurate statistics about lots of things are a problem. So what I'd like to argue is that we actually can do a lot with meaningful privacy, with sort of pretty rigorous, with rigorous statements about what is being learned and what is not, or how little is being learned. And I'm going to present sort of one framework for thinking about this problem, which is differential privacy. I would love to see other good ones of similar level of rigor. So the case I'll try to make is that, in fact, we can sort of try to nail down this idea of what it means, this idea of what it means to not allow these types of attacks fairly precisely, and that there are lots of interesting things we can do, lots of interesting data analysis that we can do, subject to rigorous limits on what is leaked. But that said, there remains a gap between the things, in many settings, there remains a gap between the things we kind of know how to analyze the information leakage of, and I would argue we should be fairly comfortable with, and places where we know that there's a serious problem and that these attacks will work. Understanding that space is an interesting question, and I think there's still much more to be said there. I think basically but I'm sort of trying to anticipate the rest of the tutorial. So let me maybe let me come back to your question, if that's okay. So another type of attack that comes up are what are called membership tests, and these were, an example of this was provided in a paper by Niels Homer and some other biologists, where they looked at statistics that were published about a type of clinical study, a genome-wide association study. And the thing that they noticed there was that even with very, very little information about the data set, if you released lots of high-dimensional summaries about the data set, and if an attacker with a little bit of knowledge of the population from which the data set was drawn was able to check if a particular person was in the data set. And in this context, we're talking about a clinical study about, say, some genetic disease, something that's correlated to genetic variation. And it was possible to figure out if a person was in the study or not, and if so, if they participated as a case or a control, meaning if they had the disease or didn't. And so, yeah, membership and just knowing if somebody is in a data set or not is already can already be quite sensitive. This came up earlier with the mental health example, right? Or just knowing that someone is in the national registry of some kind is an issue, and no-fly list are another example. Oops, sorry. Certain types of face recognition data sets could be a problem. And if statistics are broken down by category for a certain population, if they're broken down by ethnic group or something like that, then you learn which category the person is in.
Can I
Yeah.
be specific about this?
Sure.
Do you mean it's possible to test any particular individual to see if they are a member, or do you mean it's possible to identify that some people are members?
It means the first one. So roughly in this context, what it meant, in the context of this particular genome clinical study.
He wasn't talking about genomics, he was talking about a forensic mix. And this is Homer et al.?
Homer et al. was talking, they had two contexts in mind, right?
Right. There wasn't a control group. There was population statistics from HapMap. And the question was whether you were a member of the case group, whether you were in the study.
Okay, I remember the paper differently, but all right. In any case.
And similarly for the forensic mix, were you at the crime
Right.
scene?
So essentially, what it would allow you to do is, if I know a sufficiently large subset of your genome, I could tell if you were in this study. And for actually many people's genomes are public information. There are various places you can contribute your genetic information sort of voluntarily. And so for those people, you'd actually just be able to figure out whether or not they were in the study or not. With for each one with high probability. There's some, these are probabilistic tests, there's some false positive rate, false negative rate, but those rates are small. Okay, Cynthia is going to talk more about this, this broad topic in her talk on whenever your talk is, later in the week. But I'll just mention that she'll be talking, among other things, about some recent work that we did on making these tests more robust even to noisy statistics. So I'll skip over that and just sort of summarize the discussion so far that again, too many too accurate statistics allow one to reconstruct the entire data, so they're incompatible with any kind of real privacy guarantee. And maybe the kind of meta lesson, which is this notion of aggregate, is hard to pin down. Okay, so what I'd like to talk about next is differential privacy. So that's one framework where we're sort of going to try to pin down the notion of aggregate in terms of stability to small changes in the input. And this will allow us to make sort of statements that are meaningful in the presence of arbitrary external information. And I'll be more precise about what I mean by that in a few slides. And it's led to this sort of rich algorithmic and statistical theory over the past decade, and you know, a lot of interesting research and also deployments, and I'll mention those. Okay, so this is no, it's not this part. We're not going to talk about differential privacy. All right. So differential privacy, this was formulated in a paper by Cynthia Dwork, Frank McSherry, Kobe Nissim, and myself in 2006. But it evolved from really a line of work in theoretical computer science, starting with this paper of Dinur and Nissim that I mentioned earlier, and passing through other papers of Dwork and Nissim, Blum, Dwork, McSherry, Nissim, and another work of Dwork. Okay, so the intuition that we're going to use to formulate this definition is that somehow we're going to require that changes to a particular person's data, let's say my data, should not be noticeable by users outside the system. And somehow this type of requirement is going to imply at some level that the output, whatever is released, is independent of, say, my data. And this will allow us to kind of really tightly control what types of reasoning you can do about me based on the output. Okay, so let's sort of pin things down more precisely. So imagine, so we're back to our picture earlier. We've got some sort of central algorithm that's going to process a data set. We'll think of a data set as just a list of items in some domain. So it could be a list of numbers. It could be a list of categorical variables. It could be something complicated like tax forms. But I've got sort of one of these for each person in the data set. And for now, I'll think of X as a fixed thing, not a random quantity. So we're not going to rely on any randomness in X. We will rely on randomness, but that randomness will come from the procedure that analyzes the data. Okay, so for every fixed data set, the output of this procedure is a random variable. And that randomness might come from adding noise. It might come from subsampling within the data or other kinds of more sophisticated procedures. Okay, but when we talk about probabilities, we're taking probabilities over the choices made by the algorithm, not over the data. So we're going to sort of formulate the definition via a thought experiment. We're going to imagine what would happen if we changed one person's data, or maybe if we removed a person from the data set or added a person to the data set. Okay? And we're going to ask, by how much will the distribution on outputs change? Okay? More precisely, we'll say that data set X prime is a neighbor of X if they differ in by the insertion or removal of one data point. And the requirement will be that neighboring data sets should induce closed distributions on outputs. More formally, we'll say that the algorithm A is epsilon differentially private, so I've now got a parameter epsilon in here. If for all neighbors X and X prime, so for all pairs of data sets that differ by one person's data, and for all possible subsets of outputs, the probability that A of X lands in this subset is close to the probability that A of X prime lands in this subset. Okay, so these subsets are, well, events in the probability space more generally. So, for example, if S is the subset of a subset of outcomes that is bad for me, you know, so for example, that's the subset of outcomes that lead to me being denied health insurance. Then what it says is whether or not my data are included, whether or not I'm in the data set or not, the probability that this bad thing will happen is essentially the same. Okay. Or this could also be, this event could consist of, you know, the event that could be the event that I am, successfully re-identified, or the event that, you know, the parking ticket people catch up with me and you know, send me the long list of parking tickets I haven't picked, or whatever it is. Okay. There's a variant on this, by the way, where, before I go there. So this is sort of a multiplicative notion of closeness. So you should think of, if epsilon is a lot less than 1, then e to the epsilon is basically 1 plus epsilon, right? So you should think of e to the epsilon as a number close to 1, and epsilon is telling me how far away from 1 I am. And it's formulated as, you know, it's e to the epsilon because it's a multiplicative notion. It just works better to work on a logarithmic scale. There's a variant where we also allow some very small additive perturbation, and that will come up in a couple of places, so I wanted to mention it. But generally, to get the semantics we want, delta is going to be very, very small, and epsilon will be not too small, maybe 1 in 10 or something like that. Okay, so just a few points to notice. First of all, this is a condition on the algorithm. So saying that a particular output of an algorithm is private or a particular table or something like that doesn't really make sense unless I tell you the process by which that table was generated, right? And so we're really interested in reasoning about the process and not sort of the syntax of the particular output. This definition can be interpreted as implicitly specifying a distance measure on distributions. It's a metric on probability distributions. So it's saying that the distance between the distribution of A of x and the distribution of A of x prime is small. And exactly how we measured that distance really matters in terms of the interpretation we'll be able to make of the definition. And I'll mention that. I'll talk a little bit about that later. But I just want to mention that it's important. And then a final thing, what is this epsilon? Well, it's some kind of measure of information leakage. And think of it as sort of maybe not too small, but not too small. So maybe 1 in 10 or 1 in 100, but not 1 in 2 to the 50 or something like that you might see in a cryptography talk. Okay, so we're going to be, this epsilon is going to be some sort of modest difference between these probability distributions.
If you replace epsilon, e to the epsilon by 1 plus epsilon, then it's called total variation distance in probability.
It's not, actually. So this is a much...
Not exactly, you're right.
Because, and this matters. So this controls the change in small probability events much more tightly than large probability events. That's when I said the choice of distance measured matters, that's exactly what I had in mind. Yeah?
I beg you,
Uh-oh.
in tutorials, relate that to the Bayes factor, so the statisticians...
Yeah, that's coming.
Great.
But like one thing at a time, right? Yeah. So I've got a slide on, I think, on what you want.
I hope so.
But it's in like, first I'm going to give an example to try and make things more concrete. And then, okay, so in order to make the definition more concrete, I want to just give you an example of something that satisfies the definition, just so we have like something to sink our teeth into. So we're going to look, so one way to satisfy this definition is by adding noise. Okay, and let me sort of say more. Suppose we've got some summary we want to release about our data set. So our data set is x. We've got some summary f of x that we want to release. And just imagine that summary to be a list of real numbers. There are p of them. So a very simple example would be the proportion of diabetics. There's an n missing here, sorry. So imagine that for each person I have a single bit, about the simplest thing I could imagine, and the summary I want to release is just the proportion of those bits that is 1. Right? Let's say for each person I know if they're diabetic or not, and I just want to know the proportion of diabetics in my group. Okay. So a simple approach to try and satisfy this definition would be to add some kind of noise to these summary statistics, and the question is, well, how much noise do you need to add? And we can provide an upper bound at least on this for now. The intuition is that, well, f of x can be released accurately as long as f is insensitive to changes in its individual inputs, in the inputs of individual members of the data set. Okay? So more specifically, we could sort of, given a summary we want to release, we can look at some quantity which we'll call the sensitivity of the summary, which is the maximum over all possible pairs of neighboring data sets of the difference between f of x and f of x prime. And because these are vectors, we need some measure of how big the difference is, and we'll use the 1 norm, the L1 norm. So it's just a sum of, when I change one entry in the data set, I make some change to these summaries. I'm going to add up the absolute value of the changes I made. That's my sensitivity. Okay, or the maximum over all possible changes of one person's data. That's my sensitivity. Okay, so in some sense, this sensitivity is a measure of how much this function f spreads apart data sets that are close together or doesn't. And for example, if I just took the proportion of diabetics example, its sensitivity is 1 over n, because if I've got n people in my data set and I change one person's bit, then the proportion of diabetics goes up or down by at most 1 over n. Okay, so a theorem which is easy to prove is that if you add noise proportional to this sensitivity quantity, then you get an algorithm that's differentially private. So namely, you add noise that scales, it increases with how sensitive the statistic is to changes of one person's data, and it increases with 1 over epsilon. So as epsilon goes to 0, you add more noise, which is sort of makes sense, right? The less you want to leak, the more noise you add. And this Laplace noise, the exact distribution doesn't matter here. It's some peaky Gaussian distribution, but this is the form of the distribution. It's something that decays exponentially as you move away from its mean. And the idea of this, the reason this works is that when I change one person's data, if I look at the distribution of a of x and the distribution of a of x prime, basically the distribution of a of x is going to be maybe the blue curve. The distribution of a of x prime will be something like the red curve, and the mean of the distribution will have shifted by exactly the difference between f of x and f of x prime. And this Laplace distribution is such that when you shift it by this amount, you get another distribution that's still close to the original. Okay, so for example, for the proportion of diabetics, we'd release the true proportion plus or minus some random amount of noise whose magnitude is about 1 in epsilon n. And that would satisfy this definition of epsilon differential privacy. You might ask, is 1 in epsilon n a lot or a little? Well, it depends on lots of things, but just to give some sense of calibration, if x were a random sample from a large underlying population, then you'd expect to get just due to sampling, you'd expect the difference between the sample mean and the population mean to be on the order of about 1 over square root of n. And so the noise that you're adding for privacy goes to 0 much more quickly with n than does just the sort of sampling noise. And so in some asymptotic sense, once you've got enough data, the thing you're releasing is as good as the real proportion for statistical inference. Okay. How good, of course, depends on n and epsilon. But this is just to give you a sense of how it looks. I'm going to skip that slide. All right. So let me talk a little bit more about the interpretation of this definition. So first, some sort of just useful properties that the definition satisfies. So one thing that's nice about it is that it satisfies a nice composition property. So if I've got a sequence of algorithms, I want to run a sequence of algorithms, each of which is epsilon differentially private. Even if those algorithms are chosen, like the ith algorithm is chosen based on the outputs of the first I-1 algorithms. If I've got a sequence of analyses I do, each of which is epsilon delta differentially private, then jointly their sort of joint output is also differentially private, and the privacy parameters degrade gracefully, so they can be bounded by, they increase by at most a factor of k, and in fact, depending on exactly the relation between the different parameters, you'll often get scaling that's more like a factor of square root of k. Okay, so I've dropped a couple of constants in this expression to make it readable, but basically the leakage you're getting, these parameters increase sublinearly with the number of analyses you do in this particular example, or the epsilon parameter increases sublinear.
How did you go from k to square root of k?
So this is really two theorem statements. One is that this joint output satisfies k epsilon, k delta differential privacy. And the second theorem is the joint output satisfies epsilon prime delta prime differential privacy, where epsilon prime is about epsilon squared of k, and delta prime is about k times delta.
This is a union bound or something.
The first one is the first one is very straightforward. The second one is a much more involved argument. But it basically boils down, if you want to know the technical details, right? So it basically goes by first getting a tighter bound on the KL divergence between A of x and A of x prime, and using that in some sort of concentration argument. And I'm happy to go over it maybe offline. And Cynthia is also a good person to ask, so she's the D in DRV. That's Cynthia Dwork, Guy Rothblum, and Salil Vidhan.
It's nicely done in the textbook, too.
It's nicely done in the textbook, too. I agree. Okay, so another property that this definition satisfies is post-processing, which means the following thing. If I've got an algorithm which is differentially private, then anything I produce from the output of the algorithm is also differentially private. Okay. So all it says is that this measure of information leakage we're using doesn't increase in weird ways when you sort of do things with the output, which is, on one hand, a very logical statement. Like any reasonable measure of information leakage should not be increased by transforming the output. But actually, lots of sort of attempts to pin down measures of leakage for this type of privacy and statistical databases don't satisfy. So these two properties taken together give us sort of mean that they give us in some sense a design toolbox, because it means that if we want to design differentially private analyses, we can design them modularly by starting with little pieces that are differentially private and putting them together. It also means that if I've got the same data or related data sets being analyzed in different places, that I don't get weird interference effects from their analyses that are published by about these two data sets. Okay, it gives us sort of this graceful degradation of privacy. And the last thing I want to say is that this notion of privacy also gives us a meaningful guarantee, no matter what the adversary knew ahead of time about the data before seeing the output. Okay, and let me try to pin that down a little more precisely. So, okay, here's what you might want from a notion of privacy in statistical data sets. What you might want is the following. You might want to be able to say that whatever you believed about me before seeing the results of this released information, before seeing the results of this analysis, you believe the same thing about me after seeing the results of the analysis. Okay? And in fact, Torre Delineus was a statistician working on statistical data privacy in the 70s and 80s, and he sort of articulated a desideratum pretty much exactly like this, saying this should be the goal of the privacy protections we provide. Okay. And I'd like to convince you that this goal is too ambitious, and it has nothing to do with differential privacy or the specifics of any particular privacy definition. It just has to do with the fact that we really are trying to release some things about the data set. Okay, and it's impossible because of a sort of, this is the wrong word, attack here. It's impossible because of the fact that any useful, statistically useful output about the data set is going to tell me about correlations that are present in the data. And those correlations can leak information about individuals in the data, and in fact, they must. And here, oh, I don't have the example. I'm sorry, this is the wrong version of the slide, not the one I wanted to use. But I'll give you the example verbally. So imagine that you knew ahead of time, before looking at the output of it, before seeing the output of my algorithm, that I smoke. Okay? And now you see the output of some clinical study, and that clinical study shows a strong link between smoking and certain forms of cancer. Okay? Now, assuming you trust that the study was done properly, you will conclude about me that I'm at a higher risk for cancer than you initially thought. Okay? And as such, you really have learned something about me. There's this clinical study. It demonstrates, or maybe a sequence of clinical studies that demonstrate a link between smoking and certain forms of cancer. You really should charge me more for health insurance if you're a health insurance company and you're interested in making money. Of course, we can argue whether or not that's what health insurance companies should do, but you really have learned something about me. You've learned that I'm at a higher risk for cancer than you initially thought. But in some sense, the reason you learned about me was not because my data were in the data set, right? You could have learned that about me even if I lived nowhere near where the study was done, right? And so what you've learned is not something, I mean, you have learned something about me, but you learned it about me not because I was in the data, but because because you've learned this sort of fact about human biology. And this type of thing is sort of unavoidable. So this was formulated in a few places, amongst others in a paper by Dork and Orr. But what differential privacy guarantees is something weaker, but sort of I think as strong as one could hope for in this for this type of guarantee. It says no matter what you know ahead of time about me, you'll learn almost the same things about me whether or not my data are used. Okay? So it's not that you learn nothing about me. It's just whatever you learn about me is not because my data were in the data set. You learn about me because of some other thing going on that you're learning, some more global feature that you're learning about. Okay? And now to satisfy John's request, let me sort of put this in sort of more Bayesian terms. This is sort of another interpretation of what I just said, a more mathematical one. So let's try and sort of nail down the English language terms on that previous slide. What you know about me ahead of time, or what you know about the data ahead of time, we can encode that via some kind of prior distribution on the data. The conclusions you draw about individual I, let's say that's me, on a given output, we can encode that via or formalize that via the posterior distribution on the ith entry of the data set, conditioned on the output being equal to a certain value. And now we can consider sort of two experiments, two thought experiments. And the first thought experiment is real life, where we just run the algorithm on the data. In the other experiment, experiment I, we run the data without person I in the data set. So we'll just take person I and just remove them and replace their data with garbage. And the thing you can say about differential privacy is that the posterior distribution on xi conditioned on a particular output A is the same is roughly the same in these two experiments with very high probability, where the delta, that's where this delta comes in. But if you set delta 0, then you can ignore this part. Okay, so pictorially, you're sort of imagining a Bayesian attacker who will either run Bayes' rule assuming that my data were used in the experiment, and the other one where my data were not used. Sorry, that should be an I there. I don't know. It got screwed up. That should be a minus I. I'm sorry. And in both cases, the two posterior distributions which the attacker will construct will be very close with high probability. So for this type of theorem to go through, we need this kind of multiplicative notion of closeness that we had. If you tried to use total variation distance, as you suggest, we actually need the multiplicative change in probability. Total variation distance doesn't play well with Bayes' rule. So this is a sort of a more formal version of the statement on the previous slide. And if this is appealing to you, great. And if not, we can go back to what I said before, which is that you learn almost the same things about me, whether or not my data were used. Okay, so that's the guarantee that's provided. Okay, so let me just say that there have been a bunch of, so the definition I've provided is sort of one that arose essentially in 2006. There were some predecessors that are roughly similar. There are some various approximate variants. There are lots of variations on this theme where people have looked at, variations where you introduce some additional distributional assumptions on the data, generalizations of one kind or another. People have also looked at sort of trying to, rather than assuming that all the data is collected in one place, you imagine a more distributed model, and there are variations of how you might want to do that. And I'm not going to go through all these variations. I just want you to know they exist. But they sort of this formulating a definition leads us to this sort of basic question. So if we formulate, require privacy. The requirement we want for privacy is that a change in one input leads to a small change in the output distribution on our algorithm. This leads us to the basic question: what can we do subject to this constraint? I can now think of this as just a constraint on the types of analyses I'm going to allow. And at that point, once we've got a definition we're satisfied, we're free to work with any algorithm that we can come up with that satisfies the constraint. Right? So one of the benefits of sort of separating the definition we're after from the particular solution is it gives us a lot more flexibility in choosing the solution. And there's been a lot of interesting recent work in different fields. There's a lot in statistics, data mining, machine learning, etc. So across several fields, looking at basically designing differentially private algorithms to do different things. And it's really, at this point, a fairly broad and active field. I mean, there's a lot of work on algorithmic tools and techniques. There's work on sort of various foundational theoretical questions, feasibility results, and convergence rates, and stuff like that. There's also some really nice work on kind of design tools that allow us to implement these algorithms more reliably and more easily. There's work on algorithms for very specific applications, and also some connections to formulation of policy where differential privacy, or the natural language version of differential privacy, is used as a standard. And I'll mention some work going on at Harvard along those lines in the Privacy Tools project. And I don't know if these statistics are meaningful, but I did a quick search on Google Scholar. There are something like 460 articles in Google Scholar with differential privacy in the title. So it certainly received a fair amount of information, a fair amount of attention. And then if you include the full text, then sort of well into the thousands. and it's also led to a number of sort of real data products. So the Rapport project is running at Google, so it's instrumented. They've instrumented the Chrome browser for reporting, differentially privately reporting statistics about browser settings. So there's a sort of a real sense in which 1 in 4 web browsers use differential privacy. Apple recently announced they'd be doing something similar for collecting information from smartphones. There was a research group that released a bunch of password data collected from Yahoo users differentially privately, data that previously was simply unavailable for research except by one person. So this made those same summary statistics broadly available now. They're publicly available. And the census has a number of, well, this is the data product I know about. It's called On the Map. And maybe, John can tell us at the coffee break about other things going on at the census. I'm not.
Or tomorrow's talk.
Sorry? Or in tomorrow's talk, right. So John will.
Password data.
Oh, what's it's, in this case, it's frequency statistics about the types of passwords Yahoo users use to secure their accounts. And exactly which statistics are provided, I don't actually recall.
I think it's a frequency list. So imagine that people aren't all that original. There are many people who choose the same password. So imagine that you have sorted the passwords in terms of their frequencies. And the true frequency list is precisely the frequencies, but not the passwords themselves. The list of frequencies, but not the passwords themselves. And then what's released is a differentially private version of that.
What's more interesting is the principle. Like I saw in a movie, people do passwords with the names of their children or grandchildren or something like this. But there's no way of knowing these names.
So we can look. So the researcher in question, Joe Bono, actually got his PhD here with Ross Anderson, I'm pretty sure. So he did his PhD a number of years ago on how people choose and use passwords. And what he kept on getting requests for access to the data he used. And so he teamed up with Anupam Datta and Jeremiah Blocky to write this paper that's cited here. And one thing is, basically, they ensured that they would provide a superset of the statistics that were necessary to write Bono's PhD thesis. So that's kind of a certificate of like whatever was released was sufficiently interesting to allow, and to support a well-cited and informative research project. Now, of course, that doesn't mean it allows for computing everything everyone would possibly want to know. As we know, that's difficult. Okay. All right. So at this point, we've seen sort of some of the obstacles that arise. We've seen a definition, differential privacy. We've seen one thing that satisfies it, which is when just additive noise. In the second part of the tutorial, I'd like to give you more examples of things that satisfy this definition and sort of creative ways that they can be applied. But for now, we should stop and take a break for coffee. Yeah.